and have been testing and developing it ever since. It's an amazing machine. Rami and Ala can tell you all about it. They've seen it, of course. It can either scan 2 plates at once. That's what the 2 white squares are showing you in the foreground of the image. That's where the plates are loaded. Or it can do 1 single large plate. And it can scan 2 plates, which is the normal way we're using this, all but 30,000 of the plates, these 8 by 10 inch or 25 by 30 centimeter plates. We can do 2 plates in just 90 seconds. So very, very fast and very, very accurate, very precise. Next slide. So very quickly, we have a massive pipeline, computer pipeline to process the data. So let me just mention here that we are not simply only scanning the plates to digitize them. On the fly, every night, after a day's worth of processing 400 plates, we reduce all the data. All the data is reduced. We have magnitudes coming out the other end. That's brightness measurements of every star that's resolved on every plate. So it's an enormous amount of data. This pipeline, which you can look at later, and which we could describe, is very abbreviated, the many, many steps that are done. If you look at the lower right end of this pipeline, you see something called logbooks, and that's where we are very much looking forward to help from AUC. That allows us to get the metadata, or the data that tell us about each plate, like when it was exposed, for how long it was exposed, what kind of filters were used, and those data we need help from data entry. Let's go on. So in the next slide, I'm showing you the sky coverage so far with ASH. And you see these color-coded regions of the sky. This map is in what we call galactic coordinates. So at the top of the map, up at what's like the North Pole, is the North Galactic Pole. The equator is across the middle of this map. You can see there's not much coverage in the galactic equator, just little bits and pieces. Mainly this thing called BW, which is Bada's window towards the center of the map. And what you see at the top of the map is just below the North Galactic Pole, that's NGP, you see something that's called production scanning. That's what we're doing now. So we're starting from the North Galactic Pole and doing production scanning. That means the final scanning that we're going to be doing right down to the galactic equator, and then we're going to jump down to the South Galactic Pole and back up. I'll show you this at the very end. But this is the sky coverage thus far. The data that we'll release in the end of April or early May at the latest will be the very top of the North Galactic Pole region. And these 5 developed fields, Kepler field, EW, Bada's window, LMC, M44, and 3C273, for just limited regions around each of those, because they're not completely scanned. Okay, next slide. I'm going to skip over this very quickly. This is details of how we do the photometry. That's the measurement of brightness of stars. We do it in annular rings, making use of these thousands of stars that are recorded on each and every plate, whose magnitudes, magnitude, once again, are brightness measurements. I'll stop defining that. We have so many thousands of stars that we can measure and calibrate the plate in these bullseye rings, these annular rings that you see in the image on the left, and remove spatial dependence. So this is what makes this project possible today, not possible 20 years ago, let alone the fact we didn't have computers fast enough to do this. Next slide shows you an example light curve. It's just a random star across the top, which is actually not varying in time, but you can see individual error bars that show you the uncertainties on the measurements. They're typically 0.1 of a magnitude. That means we measure brightness to 10% uncertainty. Next slide. Okay, I'm now going to quickly go through a few example science discoveries, and I should probably go through these very quickly because they all would require much more time than we have. This one I'm showing you here is showing a very unexpected behavior in ordinary red giant stars, only of a very particular temperature. All these K spectral quantities, K giants, or K3 in fact, and my former student Suman Tang found this remarkable behavior back in about 2010. There's been several papers on this. It shows us that we don't understand a phase of stellar evolution, red giants, as well as we thought we did. Rather fundamental stuff. Next slide shows you an example of a phenomena that we had never seen before. There is a process that's very important in astronomy today that Harvad told some of you about. We call it accretion, when matter falls on an astronomical object, usually in a binary system. But here in the upper right of this slide, you see a schematic of what is a binary star system, one that was known long ago as a variable. It's called Ku sig, the blue lettering in the upper left. What wasn't known is that back in 1901, you look on the light curve on the top and the blow up or the detail of it down to the lower left, the star got dimmer by roughly a half a magnitude, not an enormous amount, and we've reconstructed what must have happened in 1901. Dust was actually transferred from one star to the other. We've never seen dust accretion, so rather remarkable that this is something that you can find. Here's another discovery. This one is even more fundamental. There you see on the light curve on the top, a star that got brighter back, and I should put dates across this. I need to replace this light curve showing you the dates. But this was in roughly 1940, and the star got brighter by a magnitude, actually almost 2 magnitudes, and then faded over 10 years. You see the 10-year fading. What happened in this star, which is also a binary system, that's what the middle plot is showing you. Those red dots are actually dash measurements of the variation in phase, and there isn't time to talk about that just now, but Ala can explain this to you. What this turns out to be is a nova, but a very unusual kind of nova that we call a symbiotic nova. There are only a few of these previously known. Here we have discovered in this very limited scanning another example. And this is of potentially really fundamental importance because it may tell us about the origin of supernova 1A explosions, which is a very, very hot topic in astronomy. Finally, something that I'm particularly interested in, a few slides on black holes in binaries. Here's an example, here's an image showing you the region of sky containing one of these black holes. These black holes are very unusual. They undergo nova-like outbursts. And what we wanted to do with DASH, and we're now able to begin doing, is ask the question, how often do they go off? Because they are very rare phenomena and only on for a very short time. So here we find for this first object, which is a very famous microquasar, 1655-40, if you look at these images, you can see that they're in the green circle, the upper green circle. Don't worry about the lower one. That's another object that we were looking for. The upper green circle, you can see a star in the middle of that circle that was there on August 27 and August 28 of 1945, not there on September 30, and not there on June 16. And so this is exciting to us. This is an example of an outburst of this system. This is the first time we've seen an historical outburst on any of these black holes except for 2, which are shown in the first bullet here, that have been seen from the Harvard plates, in fact. But now we can systematically look for these. And since we now have 25 black hole systems, there is a huge project that we will be doing to study how often these things go off. And so there are several others, very quickly, that have gone off. Here's one with a very strange name, B4641 Sagittarius. It's near the center of our galaxy, only very completely scanned, with a bright peak, as you can see, back in 1900, very similar to what it was doing in 2001, so exactly 100 years. There's nothing special about 100 years, but showing you that these are very rare outbursts, and you need a long time to be able to see them. Here's one more, which is a very exciting object because it's not in the disk of our galaxy, it's up in the halo. And you see in the points that are circled, all those downward pointing V's are upper limits, that this thing popped off in 1928. Here's a blow up of the light curve. I've clicked the slide, Ala, so you should see the expanded version of the light curve. showing these magnitude measurements in 1928. And so what do we have at the end of the day with only less than 10% of the plates? We've got 4 of these things that have been discovered with DASH. Here you can see their historical outbursts, and on the left side, the X-ray discovery is when, in the modern era, with X-ray satellites, we have found these things to be black holes, and we have found them only because they've brightened enormously. So this is going to allow us, when we're done, it'll be, unfortunately, several years before we're done, until we've scanned all the plates, but already we can say something very interesting about how many of these there must be in the galaxy, because if they only go off once every 100 years, we are only seeing a very small fraction of the things. Okay, next slide. And that is to quickly finish up with something on a new class of transients that I'll show you one example of, where we're now looking for not stars that we already knew are variables, but new things that we've never seen before. And so my new graduate student, George Miller, has started this project. It's looking very exciting already. We're finding, here's a detailed light curve that shows, I hope Al is on the same slide I am. I've advanced now to a slide calling extreme dash transients in the halo. Al?
Yes, yes.
And it shows you a light curve in 1935, just 3 points being shown, that looks very similar to that last black hole system I showed you. So this may be, or it might be, an example of a new black hole system that we don't know about, but we've discovered from its optical outburst. Or it might be a very unusual class of cataclysmic variables being white, just this WZE, SEE name is at the top of this slide. So we don't know, but it's showing you that there are things to discover. I've clicked now. If you click again, Al, you'll see an image taken from the Sloan Sky Survey that shows you this same object. When it is faint, which it is all the time, its magnitude is 21.3, the G is 21.3. That's a very faint star. In DASH, it brightened up, as you can see, the blue line underneath this image, to roughly 13th magnitude. So 8 magnitudes brightening. Very, very unusual event. Okay, we'll stop here with science. And I'm going to quickly just go through one example of a quasar. Here's 3C273, showing you that its 100-year light curve is very well measured. And it's measuring, I've clicked again, Al, to show you that when we look at individual flares, we can see, keep clicking the slide, Al, you'll show a 1 magnitude flare from this quasar in only 5.5 hours back in 1949. Remarkable. So there is occasionally very high time resolution DASH data. This is very exciting to us as well. All right, let me finish with a few comments on this production scanning. What you're now looking at is a map in galactic coordinates, the longitude on the x-axis, latitude on the y-axis, showing a whole bunch of boxes. Each box is 10 by 10 degrees on the sky. And where we are today, and I can't point to it, but Al can point with his mouse or whatever, we are now scanning down to the range of roughly galactic latitude 40. So it looks like we've done nearly a quarter of the sky. Well, that's not the case, actually. We've only done half of the plates in that region because we don't have the logbooks for most of those plates. I'm coming back to that in the next slide. But what we've now done completely and are about to release is the first 2 rows, actually, of plates, of boxes here. 1 through 7, I guess. I can't see it because I'm being covered up by the image. Let's see. Yeah, 1 through 7. So 1 through 7 we're going to release, and those will be complete, very nearly complete, and that will be done in a few weeks. That's latitude 90 degrees at the very top, 275. And what this means is that you and everybody will be able to access all those data, all the images, all the magnitudes, and do science with these things. Just look at images of the sky over a 100-year time period. So let me show you now, finish up, and then I'm going to turn it over to Allison, an example of something that you as students at AUC could actually do. this is something I did literally just this weekend. I told Al on Friday or Thursday, whenever we last talked, I would start playing with this. I took a known eclipsing binary. It happens to be called TX Concrete, and the constellation Cancer. And it's a known binary with a period of roughly 0.4 days. 2.4 hours, a very close binary. It's a contact binary. The two stars are in physical contact. They're orbiting each other so quickly. And lo and behold, I'm running just software that I downloaded from the net, so you can do the same thing. Al can go looking for it. It's called Period 04. It's a very nice package doing periodic graph analysis. You can see that peak that the blue arrow is pointing to on the right. That is precisely the known binary period of this star, and it is showing that it is detected in the DASH data, over 100 years of data, at exactly the magnitude and amplitude that is known, 0.12 magnitudes, which is itself very gratifying because that's roughly our photometric error, and we're able to measure something that is only that big. Actually, that means we can measure things that are smaller. And in looking at this star, which I've never been looking for before, I found that there's a recent paper on the Astrophysics Archive. I've given you the link. Al can show you how you can find this. That claims that this star might be a triple system. It might have a third companion with a 26-year period. So we can look for that. You can look for that in the DASH data. Okay, I'm going to finish now with this quick comment about the logbooks that I told you at the beginning. And that is that we have 1,200 telescope logbooks. Those are the telescope operators were recording what they were doing in making these 500,000 glass plates over the 100-year time period. Each of the logbooks tells you for every image, every plate, what the exposure time was, the date and the time. You know, we opened the shutter of the camera at 12:02 local time, midnight, 2 minutes after midnight, or in universal time, or some of them were in sidereal time, and we'll explain all this to you. And those times are critical. I couldn't have made that last slide if we didn't know the time to minute accuracy on each plate. So this is what we need your help on. And Allison is going to show you in the next few slides that she's prepared how this would all work. So I'm going to stop here. I think this is my last slide. Let me check. Yes, it is. And I will bring up Allison's talk. Al, if you can you load up Allison's talk on your machine there?
Yes, we are going to switch now to bring up.
Okay, good. I'll do the same here. Let me get this one out of the way. And here comes Allison's talk from our side. Okay, so I've got it here, Al. Let me know if you'd like to start, and then I'll turn the camera over to Allison.
Yes.
Are you ready now?
Yeah, we have the beautiful image at the very beginning.
Okay, so look at the same here, and here's Allison, and I can advance the slides for you, or you can just, okay, go for it.
Hello, nice to talk to you today. Hi, hello. Hi, Rami.
Hi.
I'm Allison. I am the curator of the plate collection, as Josh indicated. I don't know how well you can see, but I'm holding up a sample plate, the jacket, and there's a lot of writing on the outside of the jacket and even writing on the plate itself. So this very important information, but what is in the logbook is the most important because it gives important start and stop time so that we can calculate Julian dates accurately. Here's a sample of what a logbook looks like for the series that you would be typing in, which is the X series, which is a 13-inch refractor we call the Boyden, and it was sent to Peru in 1892, and that's when you would be starting to type. So let me start. This is data conversion is simply what we talk about in terms of converting script data into typed data. So we can go to the next slide, Al. All right, so the blue line, it describes the record from one plate, all of the information. Next slide. We don't need all of the information that is in the logbook. That would be too much work and really non-essential. So we only need information from 10 columns, which the arrows indicate. I'll go column by column now. Next slide. This is the first column describes the page from the logbook. In this case, it's page 14. So that's all you would put in that column, is just the page number.
This is all on an Excel spreadsheet.
Yes, I'm sorry. It's an Excel.
Easy.
I'll show you the final product or a sample of it at the end. So now we go to the next slide. This is parameters for entry of column 2. Is that where you are, Al?
Yes, we are at column 2.
Good. Okay, I'm just going to move this so you can see which slide he's on.
This here. Want to get this right?
Yeah, great. Okay, that's perfect.
Yeah.
So column 2 describes the number of each plate. Now, the plates are numbered chronologically, so they just simply would go in order, in this case 90, 94, 95, 96. So all you do is put in the plate number. You don't have to worry about the series name, because the file name indicates which telescope that number is allied with. So the next slide. Okay, column 3 describes the class. The class is simply a name that we used at Harvard to describe the emulsion sensitivity, whether it was blue sensitive, which would be L, yellow sensitive is L1, red sensitive is L2, or a multiple variation of that. So M is multiple. So a red plate that's a multiple exposure, in other words, they either we're photographing 2 different positions in the sky or the same position repeated over and over again. But a multiple plate in the red would be M2. F is focus, etc. T is test. So, and you just enter that in, and we don't use superscripts. We just use a numeric indication for 2 or 1. So the next slide is column 4, right ascension. Something you're probably familiar with, and we simply use a space bar as the delimiter between the hour and the minutes. So it could be 0 space 30 would be, I think that's what this says here. All right, next slide is column 5, declination. We sometimes go to tenths, but often not. So in this case, it's simply minus 73. Also,
let me just make a quick comment. These are very crude positions that the plate was taken at, but it's good enough for us because we independently measure in our analysis software the very precise position to arc-second accuracy. So we just need a rough starting knowledge. We don't even actually need that. We can determine the position totally blindly, but we want you to record what is written on the plate jacket. But if you're wondering why we could be happy with just degrees, that's the reason.
Yeah. And also, historically, this logbook is 1929 that you're looking at, so tenths of a degree was not too bad. So we'll go now to the next slide. This is column 6. This is the start time, the exposure, and it's expressed, like a time in minutes and hours. So simply a numeral, a space bar, and then the minutes. Very straightforward. Sometimes in seconds, as you can see at the bottom. When I give an example here, it's 5 hours, 33 minutes, 44 seconds, with just a space bar as a delimiter. Next slide. This is the hour angle, so the angle of the telescope. For those of you that are unfamiliar with this, it appears to look like a standard time observation, followed by east or west. So the top line, if I can read it here, I think it's 2 space 04 W. And you don't have to use a capital because that saves a keystroke. Oh, 224, excuse me. All right, the next slide. Yes. Did we lose them?
Are you still with us now?
We
Can you hear
are,
us?
we are at column 8. Column 8.
Okay, very good. Yeah.
Yes.
Great. All right, and just like the stop time, we have a start time, so that's very straightforward. This is why by the way, we're typing in from the logbook so that we can have more accurate description of time. Next slide. Column 9 is the length of the exposure, usually expressed in minutes. But if anything else is indicated in the logbook, you would type that in as it's written. Sometimes they'll have exposures in seconds. Okay, next slide. This is the date of the plate. A little bit more complicated, and this sample here is after 1926 when they changed the regimen that they used for expressing date. In other words, on this example, if you can see it, it's across a night in which they're giving 2 dates. In the logbooks that you'll be typing in, it's simply a single number, December 12, October 19, something like that. And when I will explain in greater detail how you would take an exposure that was taken from December 31st into January. That's a little bit more complicated. So you'll also have a PowerPoint available to use as you're typing so that you can refer back to it until you get to where it's comfortable. All right, next slide. All right, this is a sample log page for the logbook that is photographed in front of you. And you see it's page, plate, class, red ascension, depth, start time, power angle, stop time, length of exposure, and the date. So fairly straightforward, but you will, I think, find it fairly interesting to immerse yourself in how they recorded data in the 1890s or in 1910, whatever it is you're working on, the obsession with weather, and you will also find interesting things in the X that you'll be doing. They sometimes would turn the telescope at the mountains and take landscape views. So we'll deal with that as it happens. All right, next slide is just advice. We can go over this in greater detail if you're actually doing it, but we've had a lot of volunteers doing this over the years, primarily in a famous museum in New York City, the American Museum of Natural History, and we have local volunteers doing as well. So these are just individual pieces of advice that help make sure that people are typing in the same way so that then when we process the data into the database, it's uniform and we don't have as much correction to do. So that's it from my end. I don't know if you have any questions or...
Great. This is very useful, Alison, and I think it shows people what are your expectations. So I think that what we would need to know is getting access to the covers that we take those numbers to enter the Excel. How are we going to go about getting these?
I'll send you the link. It's all available on our website,
okay,
which is currently having problems today. That's just an individual glitch, not typical. But I'll send you a link, and then you simply would go to the proper telescope, in this case the X, and then I don't know how you will handle it on your end. You could give each person typing a separate logbook or half of a logbook, and they would do an Excel up through half or the entire thing. You can separate it out as you parse it out as you wish. Wait until I've given you a little bit more precise PowerPoint, simply because this is old enough, 1892, and they were taking a lot of spectra on this telescope. So some of the handwriting would be very difficult for you to understand. So I'm going to take photographs of individual things so that you understand that says spectra or L. And that PowerPoint will be a little bit more for the individual as they're typing.
Okay.
Or we could start with later plates, things are easier to read, and get people used to the whole process, and then go back to the more difficult ones later.
That's true. Mm-hmm.
I think maybe that's a easier way to go. But
Okay.
I think, Al, from your side,
Yes.
you can let us know on what schedule and how many students are interested and able to work on this, and we can organize exactly how to do it, in the optimum way.
Sure, good. I'd like to open here the floor if any of you had any questions or comments. Any questions or comments? It's very straightforward, so I think it's quite interesting. Maybe if Josh could give us a little bit about the prospects of Dash. What are some of the interesting results that would come?
So the interesting results, well, I showed you some. The black hole binaries is very exciting because we, wanted to know this recurrence timescale for the last 30 years since we've known these were black holes, and now we find we have a way to measure this. But there really is an enormous range of things that one can expect for new discovery from these plates. I showed you just a few examples, from everything from normal stars, things that we thought we understood, red giant stars that doing things that we've never seen before, to how rapidly quasars can vary, which tells us how massive their supermassive black holes are. So it's a very broad range of science.
Great.
That we can expect.
Yes, great. Any comment? Rami has a question. Yes.
Hi, Alison.
Tommy.
How are you? I just had a question about the comments. Sometimes in the logbooks they add like comments, small comments after the date. So
Yes.
should we write these comments in, or should we?
We've been leaving them out unless it would explain a problem with the exposure. For instance, if it explains that the exposure was interrupted by clouds sometimes, and then we know that we can expect a multiple exposure, or anything that you think would explain a problem with the plate that might affect the processing of photometry and astrometry. So there's some of your own judgment involved there, but for the most part, we leave the comments out.
Okay.
The most important thing that we need from these logbooks are really just two numbers. We need the date, and if there's any confusion about, as Alison was saying, that two dates are given, that usually means that it's, October 12 to October 13 or whatever. So that date is crucial. And then the start exposure time is the other crucial thing. Obviously, we very much want to have the duration of the exposure as well, but that's actually less important because we can infer a lot about how long the exposure was from seeing how deep the plate goes, and all of that we compute on the fly with our software. So the third most important number is the duration. First is the date, second is the start time, and the third is the stop time. And everything else really is of less importance. The class that Alison told you about in the beginning is very nice to have, but if you can't read the writing or something, then you can leave it blank.
Out, yeah.
And the comments are, as Alison just told you, interesting if they tell us something that we might need to know, but in general, they're less important. So what we're really trying to do is to get a whole bunch of students who will find this interesting to work on to help us get these things done, because the reason that we've only got data completely scanned and processed for the very top row of that row of boxes I showed you on my second to the last slide is that we don't have the logbooks done.
Yeah.
So we have this enormous need. We've known this for years, and this doesn't mean the project stopped, but it means that we go not nearly as quickly and efficiently if we don't have this information.
Yeah. We have people helping us scan, and what we do is we divert them to typing. So we're not getting as much scanning done in that case.
So if you can find colleagues, high school students, other people who might find this exciting to do this for a while, this would be very, very helpful. And in return, then you get used to looking at what these data look like. Well, you have to do that separately on our website. And as I said, the data will be released very soon. You'll have access to a lot of data to look at. But we need a lot of people doing this, and it would be wonderful to have as many of you as are interested do some of this.
Yes, and we actually have here groups not only from AUC, but we have groups from Cairo University, from Harvad, and from other universities as well. So I think
that's fine. I should have mentioned that, and that's great to hear.
Yeah.
So.
Right, but let me ask you, how about making sure that a given lookbook that one is typing from is not being worked on by somebody else?
Well, that's going to be up to you to assign, because we can't keep track of who's doing what there at either AUC or Cairo University or anybody else working.
Yeah.
It will require. I think what we'll do to we could have a long discussion about this, but Allison will set up with you, Al, I think, once you have some idea of how you want to start this and how many students are going to begin, I think we can set up a very simple system of just by email of every week, some kind of a log sheet comes back here, one email, and saying, exactly what's been done. And we can think of the easiest way to do this for you and for us to keep track of what's being done. And for example, when I said that let's do the easier plates first so that everybody gets used to this, we can coordinate that with you and say, all right, now I can see you've got 6 students that are really moving along, and they're doing a great job, and we can have maybe 3 of them go back and tackle some of these ones from the 1890s that are a little more difficult to read. But we can, I think, just a weekly email or 2 back and forth, we can keep track of who's doing what. Should be very simple.
We can keep track for those who are working from within Egypt, but I meant if you have others working in the US
sorry.
Making sure that there are no duplications.
Well, we are only sending you, we would be assigning you this X series, which is, by the way, a very interesting telescope. You should, this is very important for the science, because this is a relatively big telescope. 13 inches is only like this, right? It's not a big telescope by today's standards, but in 1900, this was one of the biggest telescopes in the world.
45 arc seconds per millimeter.
Yeah, so it's very high resolution also.
Yeah.
So this is beautiful data,
and it's still in South Africa. It's still there. So
it's been in the Southern Hemisphere except in the very beginning. But anyway, we don't give the same or assign the same logbook to more than one group. So there's no confusion about somebody else doing this.
Good. Okay.
That's right.
All right.
So what we usually do is we keep an Excel spreadsheet, explaining who is doing what, and then once we receive data, we keep a spreadsheet indicating what we've received and comparing back and forth. Then we know what's happening.
Good. Okay. Any comments? Any questions? Great. I think everyone here is ready to work, so I will look forward to getting the online link. And if you would like to add anything, I think we are all done. And maybe we can, since we have groups here coming from various places, I'd like to bring them here to line up next to your image so that we can take a group photo with you. I think that's something that everybody would like to do. So come here.
Okay. That would be nice.
Yes?
Yeah.
Come here, let's line up here. And then,
okay.
Wonderful.